Hello wizards, welcome back to the Machine Learning at Microsoft YouTube channel. It's a paper review call again. It's a weekly opportunity for someone at Microsoft to take a machine learning paper from the literature and to dissect it surgically, clinically. We want to have these calls as a forcing function for all of us to get really, really good at machine learning, because the best way to get good at machine learning is reading papers. And in a way, it makes you a bit cynical as well, because when you read a lot of scientific papers, it makes you realize how challenging machine learning research is, and actually how challenging the scientific method is in general. It's so difficult to conduct experiments in a rigorous way. And if you do so, the complexity spirals out of control. And when you read enough of these papers, you start to pick up on patterns and you learn how to critically appraise what's going on. And that's kind of what these calls are all about. Now, today we have Karol Zak. Karol is an absolute legend. He's worked on my team on quite a few projects over the last year or so, and he's an expert at computer vision. We've done some really exciting things recently, like detecting geometry from satellite images, and even more recently, predicting when football players take a shot on the goal. Karol's got an amazing history. He's been at Microsoft for about 6 years or so, and he's got a degree in computer science. The paper that Karol's talking about today is called Learning Temporal Spatial Relationships Using 3D Convolutional Neural Networks. Now, this was a really interesting kind of breakthrough paper. It came around 2015, and it was the first paper to use an end-to-end 3D convolutional neural network. So it was maintaining the temporal information through the entire life cycle of the convolutional neural network. In previous approaches, the temporal information has been collapsed or kind of removed much earlier on. So some of the newer approaches to video action detection have really kind of signed on to this fact that the time information is critically important. And some of the newer methods kind of build on this further by having skip connections in time, or having a memory bank in time, or having a slow kind of channel and a fast channel. But this was the first kind of approach to really kind of prioritize the temporal information in video action detection. I hope you enjoy the call today. It was absolutely brilliant. We had about 125 people join the call internally here at Microsoft. We had some really, really good questions on the call. Remember to like, comment, and subscribe, and I'll see you back here next week. Peace out. So I'm here with Karol Zak. Karol, say hello.
Hi everyone. Hi Tim.
So Karol just did a paper review call today, and I'm really interested just to kind of know a little bit more about you, Karol. So what are your main interests in machine learning?
I'm honestly interested in machine learning as such. So anything machine learning related gets me excited. But if I would have to choose, I would say computer vision and anything related to visual recognition tasks. It's something that gets me going. And if you would ask why computer vision, I think simply because you can visualize it quite easily. So you're working with images, you're working with videos. These are things that you can easily imagine, easily visualize. So it's very interesting to know how machines, how our algorithms are seeing these images, how they perceive them, how they transform them, how they are able to understand those images and classify or detect objects on these images and so on. And another thing is that my background is software engineering. So aside of this super interesting path of building models that are better and better for any task, there's also this motion of side tasks or side problems that you need to tackle, and these are all software engineering related problems. Like when you're working with images or videos, these are high volumes of data, and now the problem is how to process it, how to do it efficiently, how not to run out of memory when you're doing it. So there's this, like I said, this mainstream of building models and getting them better and better, and all of these side tasks, these side software engineering challenges that you need to tackle on the way. So this is very, very interesting.
I completely agree with you, because I think machine learning engineering is one of the hottest tickets over the next 5 years or so, because machine learning is becoming democratized to some extent, but the real challenges are, how do you put this into production, and how do you maintain the models in production? And I mean, we recently worked on the Delta Trade project for detecting when football players take a shot on the goal, and we spent almost our entire time on that project just doing data processing.
Oh yeah, that took a lot of time. We were working with really long videos, like the whole half or the whole match, soccer match or football match, which is like 90 minutes in total. And these are really, really huge volumes of data, and you need to process them, and you need to extract all the frames from these videos and run some sort of inferencing of a bunch of different models that you came up with, do some pre-processing on the way. So it's absolutely amazing, how we are able nowadays to do such things. And yeah, this is definitely something that gets me going, and these are the challenges I love to tackle on a daily basis.
Yeah, it's so true. And machine learning software in production produces more technical debt than traditional software. So there's so much stuff you need to do around testing it and doing things around robustness and bias and so on. So I honestly think that the machine learning engineering space is going to be so exciting over the next 5 years or so. But anyway, so we're doing a paper today. The first kind of significant paper on 3D convolutional neural networks for action detection. And how did you find the experience kind of reading through this paper?
Yeah, it was definitely very, very interesting, even though it's not state of the art anymore. So there are better implementations, better solutions for this particular task. Still, this paper was so interesting. The whole idea behind this paper, how they came up with this task of creating a universal and compact video descriptor or features generator for videos. It's just simply amazing how they came up with that, how they made these points that they want to achieve, so that the model should be compact, it should be uniform. The embeddings produced by this model, this video descriptor, should be applicable to a bunch of different videos without even fine-tuning them. So, and they did it. They actually completed all of these, and they achieved tremendous accuracy and performance. So yeah, it was definitely interesting to go through that, and to dive deep into that, to write some implementations as well, to go through the pain of processing all the videos again, and to creating pipelines and so on. That was it was a great journey. I have to say.
Yeah. When I read through the paper, I must admit, one of the things that jumped out at me is because after you've read a whole bunch of scientific papers, because that's what we've been doing on these paper review calls, is you realize how difficult science is. In the natural sciences, we're trying to do experiments, like, for example, what happens if people eat a certain type of diet. And if you're studying the brain, as Matt Salvaris said on the interview last week, it's actually really, really difficult to do, because you can't shut off the rest of the brain and just study one particular piece in isolation. And in this particular paper, they were doing experiments on things like, well, how big should the convolutional kernel size be in the depth domain and the time domain? Should they be increasing in size as we go through the network, or should they be fixed, and what size should they be? And if they ran every possible type of experiment on the entire data, it would just take all of the time in the universe. So science is just this incredibly imprecise. There's so much there's so much kind of intuition, isn't there?
Yeah, absolutely. and still I think they managed to do a great work around that, because they what they did, they basically properly researched Con3D networks and how they perceive videos, how they work with spatiotemporal features, and what kind of features they extract, what do they see. So they did some deconvolutions to, investigate what these networks are actually detecting in frames. So they did a great study, and I think thanks to this research, even though it wasn't the first one talking about Conv3D, I think it was the first that did this really deep research behind it. And like you said, they investigated different sizes of kernels, different depths of networks. So yeah, I think this was definitely a breakthrough when it comes to video processing, video recognition, and Conv3D networks as well.
Yeah, and I think this was the first paper that used convolutional 3D, as in, modeling the time dimension throughout the entire network. I think in some other papers, they did use a convolutional 3D, but I think in one paper, they used cutouts, so they did a bunch of pre-processing first. This one was using the data in the original domain, so not cropping. And also it was maintaining the time dimension through the entire network, whereas I think before it had been maintained for a couple of layers in the network and then flattened out.
Yeah, exactly as you said. That was, I think, the first paper, the first research that that focused that much on that time domain, and to basically keep this temporal information overall the whole network. Yeah.
Yeah. So in terms of where action detection is going, one of the other things that jumped out at me is that we are still somewhat dependent on the two-stream approach. So all of the current architectures, we're kind of fleshing out this RGB approach using 3D convolutional neural networks. And in the newer architectures, there's this I3D, and there's a few variations on that. But in order to perform really well, you need to have a second channel using this dense trajectories, which I assume is some kind of an optical flow-based feature. And the problem for that is it's just computationally intractable to kind of compute this on a large data set.
Yeah, absolutely. That's one of the big problems behind video processing, as like we discussed before. The volumes of video data are just so huge and hard to process already. And if you throw some more computational complexity on top of that, or even more computational complexity on top of that, it's just not efficient anymore. And that's why in this paper I was talking about, that was the main focus for them, to basically come up with a simple solution that is simple to implement, it's efficient performance-wise, it's just working great, and the amazing part is that they actually achieved that, and that's very cool.
Cool, brilliant. Anyway, well, Karol, thank you so much for this pre-interview, and let's move on to the main paper call.
Yeah, thank you, Tim.
Cool.
You know that I love a practical approach. I talk code, so as usual, I prepared some samples. I prepared some implementations that will be available, and I will show off later. So I guess we'll start from few slides I prepared, just to give you a brief introduction of what we're going to be talking about today. And for that, I will try to share my screen. All right. So as I mentioned before, we will be talking about 3D convnets, and more specifically about one of the really great, really exciting research papers I found, which is called Learning Spatiotemporal Features with 3D Convolutional Networks. It's back from 2015, but it's a very interesting paper, and hopefully you're going to like it, enjoy it as much as I did researching it here. So first off, before we go to the actual paper, as usual, I want to give a brief introduction of the domain or the task that we will be trying to tackle with this approach. And the problem is called action recognition, and it's related to videos. It's in videos domain. These are some of the examples coming from popular action recognition or video data sets that are available there. I do believe there's sports 1 million over here in the middle, and the edge ones are coming from UCF 101, which I will explain later. But this gives you a brief idea of what we are trying to do. So basically, we have videos or short or long, a bit longer clips that we want to classify. We want to recognize what kind of action is represented by this specific video. So, for example, is it applying eye makeup, or is it blow drying hair, or playing flute, or whatever, or skateboarding, for example. So this is what we are trying to do. So basically, take a video, cut it into frames, and try to recognize it some way, basically classify it. Research-wise, if we look into the past of what was there, what was available, what was done by folks around the world in machine learning area, it's not everything. Obviously, it's just some of the highlights I think are most interesting, and it all starts around 2012, where they came up with this data set called UCF 101, which is basically a data set of 101 different human actions coming from videos in the wild. And for many years to come, this was a basic benchmark data set for action recognition or classification in videos domain. And another paper, which the one called 3D convolutional neural networks for human action recognition, this one, I think this was the first time somebody mentioned 3D convolutional networks and actually put them into usage. But back in then, I think there was no, there was basically not a big enough data set to actually put those convolutional 3D convolutional networks into real usage. And that's why after 2014, when they introduced, Andrei Karpathy et al. Introduced a data set called Sports 1 million, which was a data set of over 1 million videos representing 487 different classes, different sports or actions, which is huge. And the video was from the wild. Like these videos were coming from the wild, so basically they were downloaded or scrapped from the internet, more specifically from YouTube. With that data set, they also introduced some approach to do action recognition, and they came up with state-of-the-art solutions, achieving up to 65% accuracy on UCF 101 data set. But at this point, they were using only convolutional 2D networks. Everything they did was based on conv2D networks. And the paper that we'll be focusing on today, learning spatiotemporal features with 3D convolutional networks, is the one that was presented in 2015. It achieved 90% accuracy on UCF 101, so it basically beat the whole competition. It was state-of-the-art at the time, and that was the first time when they actually used 3D convnets on such a large scale. And this was it was specifically possible because they finally had a huge enough data set to really leverage these conv3D nets. And so with this paper, they basically created a uniform and compact model that was able to create features for any videos, right? So basically came up with a video descriptor of such.
Karol, could I just make one comment there? I think that if we were just using the 3D convolutional neural network with a linear classifier, this paper got about 82%.
82%.
And
Correct.
I think it was when there were 3 different networks and also the optical flow features in combination, then it got 90.4%.
Yes, that's a very good point. So that might be misleading, but when they use a very simple C3D, the basic model, basic features without any fine tuning and linear SVM on top, it gave them 82% accuracy. But the best model they created with conv3D networks came up to 90%. But yes, very, very, very good point, Tim. And obviously that was back in 2015. So it's interesting whether it was possible to actually beat that number, and they did. So in 2000, it's not. So just so you know, the paper that we'll be going through and the approach we will be going through today is not state of the art anymore. There are better performing, better scoring solutions, but this one is particularly interesting because how compact and uniform video descriptor they developed with this research. And yeah, I'm going to prove you that it is even more exciting than what has been done in following papers and researches. So in 2017, they basically beat the UCF 101 dataset with 98% accuracy, and it was done by researchers from DeepMind, from Google. And they use a network called i3D, which was, in principle, it instead of creating new conv3D architecture, they took the ImageNet one and basically inflated the kernels, the filters. So instead of using the 2D filters, they inflated them to make them 3D kernels. It's even deeper than that, but honestly, I got so interested in this one that I might do it as a follow-up paper review call to dig deeper into this subject, because it seems to be the best so far, at least for UCF dataset, and I think it's worth investigating it even more. And there's one more which is worth mentioning, because after 2017, when UCF dataset, which was like a benchmark of such, was basically done, it was beat, some new data sets started to emerge, and so researchers had to pump up their game, come up with even more brilliant ideas for models for action recognition, and then there's this paper talking about AssembleNet, which is, so far I didn't get into all the details yet, but it seems to be a very sophisticated approach. But so were the new data sets that were presented, like the charades or moments in time data sets.
So Karol, could we just sort of meditate here just for a minute, because this is super interesting. So if we kind of look at the most important features in coming up with a good video action detection system, one of the most important things seems to be data. And this i3D model, one of the reasons it works well is you get double transfer. So you take an ImageNet convolutional base, and then you blow it up in the kind of time dimension, and then you can fine tune on your own, on a data set like Sports 1 million or Kinetics, and then you can fine tune it on your own data set. So how much of the advantage comes from architecture versus data is unknown. And then most of these approaches also use a combination. So they use one channel just with some kind of three-dimensional convolutional neural network, and then they have another channel which is using these dense trajectories. And that's one of the best handcrafted features, but it's computationally intensive to run this feature. So it's very, very difficult to compute this feature for the Sports 1 million. And most of the new papers seem to be doing some kind of combination. So for example, this AssembleNet, it's doing an architecture search, and it's combining the two channels together. And some of the other newer papers are doing things like having a slow path and a fast path, and doing various skip connections between time. And most of them are kind of playing with the time dimension. And another way of achieving something similar would be doing data augmentation. So you sample your actions at different kind of times, at different frames in time, and all of these things seem to improve the results. So we're kind of at the stage now where we seem to have a kind of methodology that works, and we're just trying different combinations.
Yeah, absolutely. You brought up some really good examples of what is happening currently in that area of video action recognition. And as you said, most of the best approaches right now are using these kind of two streams. Where they both use like the RGB data, but also some pre-computed, dense flows or optical flows that they combine and kind of use as a single model. And but all these approaches seems to be very computational heavy. And that's actually one of the things that we will be tackling with this research paper we'll be talking through today, because these researchers, so Tran et al., they noticed that there's this motion of building models that are very heavy, like computational heavy, and they are not well fitted for large-scale data sets and large-scale processing of videos. In videos domain, right? So they wanted to came up with very simple and very efficient performance-wise approach, and so they did. Again, before we will get there, just to make it clear what conv3D is, just a small comparison of conv2D versus conv3D filters. And as easy as it is, conv2D layers or filters, they basically, no matter how many layers or channels you will have as an input, so you can have, let's say, an input of, 100 by 100 with 20 channels. If you run it through conv2D filters, you will always end up having a single channel output. And that's how you basically lose the temporal domain, the time domain, with this approach. Whereas in conv3D, because you have these cubes, right? So you have these 3D filters, 3D kernels. You're kind of using that, not only that spatial domain, but also that temporal, the time domain in your favor. So this seems to be, as a concept, seems to be a perfect approach for classifying videos or recognizing or detecting events in videos.
Just to add to that, because when you look at a 2D convolutional neural network, all of the response maps are volumes. But the reason you have a volume is because you have multiple filters. Because actually, if you put a volume, because every layer in a convolutional neural network is a response map, and the depth corresponds to the response maps for all the different kernels that you've learned. So if you convolve a volume against a 2D kernel, you'll always get an image as a result, which means in this context, you'll always lose the time information.
Yeah, very, very good point. And that's exactly what happens. So hopefully that gives you a brief idea why conv3D in theory might be a good thing for videos. And now off to the paper itself. So, like I said, it wasn't. Well, it's not the best performing approach anymore, but still the idea behind this paper, this whole research, for me was just brilliant, because they noticed that for this high scale data sets with this multiple videos, this high number of videos that we want to process, we need to be efficient. We need to, performance-wise, we need to be very, very efficient. And that's why they wanted to come up with a simple, like a video descriptor, features extractor network that will be performing very fast and will be compact and uniform. And once pre-trained on a big enough data set, you will be able to apply it to any other data set containing videos, hopefully. And so one of the outcomes they learned is that definitely 3D convnets are more suitable for spatiotemporal feature learning versus 2D convnets. They also discovered that small kernels like 3x3x3 are among the best performing architectures. They tested out different kernel sizes and researched that 3x3x3 is the most optimal one. And as they mentioned, the learned features, namely C3D network, so convolutional 3D network, with a simple linear classifier like a SVM classifier on top of that, outperforms state-of-the-art methods for different tasks, different data sets.
Karol, we've got a question in the chat. So the question is, what makes 3D convolutional architectures better than something like a conv2D plus an LSTM or a GRU or some recurrent neural network?
Tough question, but they actually did comparison against that. So further down the paper, there is actually a benchmark comparison against a bunch of different methods that were used at the time. And I think LSTM or 2D convolutions with LSTM on top of that was one of the approaches.
It was. So these LSTM approaches do seem to work quite well, but I think the reason CNNs are favored over RNNs in a lot of places now. And one of the kind of revolutions of CNNs is that they're so parameter efficient, and they have this beautiful idea, which is reusing the weights in multiple places. And CNNs as well can learn kind of local spatial temporal dependencies, whereas RNNs learn global dependency, as in global orderings, and they have more parameters and they're harder to train. You can't train them in parallel. But to be fair, the results for the LSTM version are in the paper, and they're not particularly bad, but all of the state-of-the-art approaches don't seem to use LSTMs at all, and I would just guess it's because they're harder to train.
Yeah, might be that. Right. So in the introduction part of this paper, authors bring up the whole, like I said, the whole idea behind this research, and the research is quite long. This research paper is really, really long and complex, and the whole idea behind this paper, this research, is that they wanted to come up with a simple and generic video descriptor, and to build such a descriptor, they came up with four very important properties that it needs to showcase. And first is generic, so it needs to be able to describe or generate features, good features for a bunch of different types of videos without even fine-tuning. It needs to be compact, so even with limited number of features, it should be able to process the videos fast and with high accuracy. it needs to be efficient. I already said that, but it needs to be efficient to compute fast. As we are working on high volumes of video data, these are like really huge files sometimes. So we need to be fast and efficient, and they achieved that. They definitely achieved that with their approach. And it needs to be simple to implement, and they definitely followed that rule throughout the whole paper, which I will show you later. They also talked through related work and what is state of the art, and it seems like they did a very, very good research in that subject. So they investigated a bunch of different solutions that were tackling either the same problem like action recognition, or different tasks, but with a similar approach. For example, using the 3D convnets and so on. But so they mentioned one paper called Improved Dense Trajectories by Wang et al. And they said that this is the current state of the art for handcraft features in action recognition for videos. But the problem, even though it performs very well, the problem is that it's very computationally intensive, and they wanted to build something light and compact and still powerful. Right. Yeah, so they came up with the thesis that 3D convnets are best suited for spatiotemporal feature learning. And so, again, but it's not like they invented 3D convnets. There were they before, but it was the first time that 3D convnets were used or trained using such a huge data set. And that's exactly when they showed the true power. In the following pages, they describe differences between 2D and 3D convolutional operations, which we already went through. So basically, they specifically point out that even though you pass in a volume of images and you use that 2D kernel on top of that, you will always end up having a flat output, right? Whereas when you use 3D convolutionals, you will get this. You will basically sustain that temporal features or time domain features. So first thing they did, to give you an overview of the research and the steps they took in the research. So they first started with UCF 101 dataset, as it's not the biggest one. It's big enough to train network, but it wasn't, the biggest at the time. So to compare against, for example, Sports 1 million, Sports 1 million was 100 times bigger when it comes to number of videos compared to UCF.
Karol, so that is the most beautiful flowchart I've ever seen in my life.
I know it's not, but thank you, Tim. I did it with my mouse, so you have to give me some credit for that. So they started off with UCF to, don't go to the biggest possible data sets from the very beginning. So they started off with UCF, and they kind of did an architecture search. So they tested out different kernels, different architectures, deeper networks, more shallow networks, and so on and so on. And they came up with a couple of architecture proposals. Best ones were achieving around 45% of accuracy. And once they had these proposals of network architectures, they took those proposals. They took Sports 1 million dataset, which was huge, and they basically trained these architecture propositions with that huge data set. And that's how they came up. They basically built their C3D video descriptor or feature extractor. And once they've done that, they use that C3D or that video descriptor to generate features for UCF dataset, applied a linear SVM on top of that, and achieve specifically 82% accuracy on UCF dataset without any fine tuning. So just using the embeddings, the features coming from running UCF dataset through C3D network and running linear SVM on top of that, they achieved 82% accuracy.
So should we take a pause here? So first of all, let's explain what fine tuning is. Fine tuning, because the beautiful thing about neural networks is they're kind of composable, and you can take models trained by other people and you can just use them directly in line, or you can train into the model. So you can kind of freeze most of the model and just unfreeze the last few layers, and then you can train into it, and that's called fine tuning. And of course you're training into it using your own domain specific corpus. So you can essentially take a sports 1 million and then you can train into the end of it using UCF 101, and that would improve the performance. But here we're not doing that. This is analogous to taking the ImageNet, like a VGG ImageNet model, and just taking the embeddings, not doing anything to them, and then just building a supervised classifier with the embeddings. So it's completely decoupling the two steps. The other thing I wanted to touch on is this architecture search. Can you look at that, the graph in the paper showing the different depths? Because I think this is really interesting, because in the 2D world, in convolutional neural networks, everybody uses 3x3 kernels. And it seems kind of interesting, doesn't it? Why would everyone use 3x3 kernels? Because it seems to be kind of like the smallest possible kernel to register a kind of positive and negative transient in two different dimensions. So the question that the authors on this paper asked is, well, how big should the depth dimension be? Should it be 3? Should it be 4? Should it be 5? Should it be increasing or decreasing? And when they did this architecture search, you can see these two graphs in the top left, they kind of plotted all the different combinations. So the depth of 1 is the blue line at the bottom. If you zoom in, and that's significantly worse than all the others. So the time information does seem to be important, but the best one is actually a depth of 3. And this is a philosophical question, out to all of you folks on the call. Why do such primitive kernel pattern sizes generalize better? Why do we not use bigger ones?
Well, one reason I always thought of was that basically every important physical equation is second order, right? And it takes 3 samples in order to get to get any approximation for a second derivative. And then if you combine that with kind of, Occam's razor, right? The simplest model tends to be preferred, all else being equal, right? So I think that's why we run across this, really.
Yeah, that's super interesting. But it does also just kind of highlight how arbitrary many of these practical papers are, because most papers in the deep learning literature now are kind of like, I'm running some empirical experiments and I've managed to beat the state of the art by a tiny little bit. And, you have to make all these arbitrary decisions like, should we, it seems to make sense if we increase, should we kind of maintain the temporal information at the beginning? Because I think on this paper, they maintain the temporal information on the max pooling layers at the beginning, and then they started to downsample the time domain, and you make all of these kind of arbitrary decisions. And of course, if you were to do an ablation study and kind of test every possible decision that you've made, it would be intractable, right? Because these experiments are so expensive.
Yeah, it's a very good point. So we were saying, so they did the architecture search on that smaller data set, and they basically trained it on sports 1 million, and that in fact was the C3D, basically the video descriptor or the feature generator that they referred to afterwards. And so, but that was not the end. So they trained the C3D descriptor, and wanted to use it as a basically video descriptor, right? So it's a feature extraction step. And if we're gonna look into detail how they trained it, because they described exactly the steps they took to pre-process the data. Because Sports 1 Million, you have to know that the videos there, some of them are quite long, so up to several minutes long, which is quite a lot when you think, about it frames wise. That's really a lot of frames. And so what they did, and again, it is kind of arbitrary how they came up with that. Not sure if they just thought like, okay, so we're going to take 5 random clips from each long video. Each of these clips will be 2 seconds long, so approximately 50 frames each. And yeah, it will be resized to 128 by 171, and that's it. Why? Well, we don't know exactly. I mean, we can think, we can make some assumptions about the resize thing, but why, just 5 random clips out of 5 random 2-second clips out of several minutes videos? We don't know that, but that's what they did for training purposes. And so
sorry to interrupt you. This raises an interesting issue with action detection in general, because some action detection seems to be quite stationary. So you can tell that someone's waving if you pull a single frame out. And similarly, with some of these video data sets, the videos can last for a couple of minutes. And if we're just pulling out 2-second chunks, we don't even know for sure that those actions will be present in those 2 seconds. So it seems quite error prone, which is why we're kind of hedging our bets and we're kind of averaging over, several chunks inside the video. But they also do this kind of data augmentation, don't they?
Oh, they do. Yes. So in the first step, they extract 5 random clips, 5 random 2-second clips from each long video. They resize them to 128 by 171. And then during training, they do this kind of data augmentation. So they randomly take 16 frames from each clip, and they randomly crop them into 112 by 112 frames. And they also apply horizontal flip on 50% of samples. And that's something they do for data augmentation purposes. And afterwards it's fit into the network, the C3D, for training purposes. And they achieved with this network, where is that? Oh, I lost it. Here it is. So they achieved on Sports 1 Million, they achieved 85% accuracy. And when you compare it to best at the time, it was 5%, lower. So basically, they didn't beat the best at the time. But what is interesting is that when they applied this same model, pre-trained on Sports 1 Million, and they applied this model to generate or extract features for different data sets, as you can see here, they actually beat the state-of-the-art solutions without any fine-tuning, if I'm correct here. So. Yeah.
And just to be clear, if there was fine-tuning, it would probably be even better. And another point to make is it was trained on the Sports 1 Million, but there's a standard split for the Sports 1 Million. So, of course, it was trained on the train split and tested on the test split.
Yep, absolutely. Yep, and so these were the results. And that's how they came up with this C3D video descriptor or features extractor. And then they use it for a bunch of different tasks and a bunch of different benchmarks and data sets. The overall architecture is fairly simple when you think about other very deep networks that we have nowadays. This one is like really, really simple. So we have first convolutional layer. It's all conv3D. So just so you know, it's all conv3D layers followed by 3D pooling. So it's conv3D, 3D pooling, conv3D, 3D pooling, then followed by 3 double convolutional layers, followed by max poolings, and at the end we have 2 dense layers followed by softmax to basically do the predictions on the class. And yeah, because it's simple, they promise the architecture to be simple, the solution to be simple to implement, and it is. In Keras, it's literally like 20 lines of code, so it's super simple to implement, which I will showcase later. And yeah, so with that C3D video descriptor, how they extracted features, you would ask. So what they did, they used that FC6 activation or activations coming from FC6 layer. So basically from this dense layer over here. So they run frames through that network. They extracted activations from FC6 layer, ran it through L2 normalization, and then applied simple linear SVM on top of that, to get the to basically have a classifier on top of these embeddings. And with that, they were basically beating or competing most of the state-of-the-art approaches at the time.
Okay, we've got a couple of questions, Karol. Ilya, do you have access to your microphone? Because we were just making that comment on why a 3 by 3 by 3. And Ilya is an absolute legend when it comes to computer vision. We're going to be doing a paper review call with Ilya soon. I don't think Ilya has access to a microphone, but he says that a 3 by 3 by 3 convolution is the smallest kernel that you can run with padding that would keep a constant size. Stacking smaller convolutions instead of big ones seems preferred to reduce the number of parameters, but keeping the same capacity, which is factorization. Priyanka also asked, is there any idea what's the motivation for the cropping? And I may be wrong, Karol, but I said it was presumably they wanted to reduce the input size, they wanted to reduce the number of parameters, and also cropping is a form of data augmentation as well, which means you can kind of blow up your training size.
Yeah, if you're talking about cropping in the training phase, that definitely was for data augmentation. So instead of passing the whole image as is, they basically took different smaller crops from different parts of the frame, and that's how they kind of augmented the data set. And as for scoring strategy or scoring pipeline, I tried to describe it here as as well as I could. So for scoring, especially on UCF 101, using C3D as features generator, it looked kind of like that. So a UCF 101 dataset is a collection of couple seconds videos, a couple second long videos representing different actions performed by human. So what they did for scoring, they basically took each video, and from each video they basically cut the video into 16 frame clips with step of 8. So every 8 frames they took 16 frames out, and they center cropped them to 112 by 112. I mean, it's not it's not really specified about the center crop. I kind of got it out of the context, but it kind of makes sense too. So yeah, center cropping, and they fit that into the C3D model to generate the embeddings, the features for all these clips, and then of course run it through L2 normalization. And so they ended.
Should we just quickly just pause on that? So the
Sure.
first thing is when you use a convolutional base, it might have been trained by some other people somewhere else, and you need to normalize your data in the same way. Otherwise, the base might behave differently. So I think on Karol's implementation, for example, he removed the mean, the color mean from the 3 channels, and of course we would have to go and check whether the original base model had the same thing done. But we have an output embedding for every single kind of sliding window of the input, and then the reason we normalize by the L2 norm. So the L2 norm just basically means the kind of the magnitude squared, and then we divide all the vectors by that. And the reason is because we're going to average all of those vectors into one. We don't want any one vector to kind of dominate the other one. So we normalize them first, and then we kind of average them all together.
Yeah, and with that we end up having per clip embeddings for each longer video. So, for example, for a long video, we can have as much as 30 embedding vectors representing cutouts from that video. And so what we need to do is basically take all those clips for a single video and take all those embeddings for a single video and average them. And that's how we come up with a single embedding vector or features vector for each video. And then we take all these videos with their feature vectors. We run it through PCA, principal component analysis, and they tested out a bunch of different dimensions for that, or a number of components. Once you have that PCA bit done, you basically fit it into a linear SVM, and that's it. That's how you build your classifier. And just wanted to point out that this is probably not the best approach. It can be done better, and they actually improved it. They improved that top classifying layers or classifying part. But what they wanted to showcase is that they were able to build a simple and compact and uniform feature extracting model, and they did that, and they were very successful on that.
Just a quick comment on the PCA. It's quite a good thing to do because the output space here was about 4096, and classical algorithms suffer from this kind of curse of dimensionality, which means when you have too many attributes, they just start performing really badly, and they overfit as well because you have so many attributes. You could kind of say, well, if attribute number 4005 is a positive value, then it must be this class. Not only that, there are computational reasons to have a more compact feature vector, because many of the algorithms, like if you look at trees, for example, the space complexity can just get out of control if you have that many attributes. So there's no reason why you shouldn't use PCA. But what we should see, though, is that if you have too few PCA dimensions, you kind of lose information. And if you have too many PCA dimensions, you get this curse of dimensionality, you get overfitting, and it just becomes computationally intractable to train a downstream model.
Yeah, and they definitely prove that their model is very compact, as is generating very good features as well, because even with PCA, 10 dimensions, resulting in 10 dimensions, they achieved almost 50%, I think, or something like that. They are around 50% of accuracy, and the best one with 500 components achieved 82% accuracy. So, dimension of 10, a vector of 10 features is basically nothing when you think about it, right? And yet they were able to build a very powerful classifications with that. So that only proves that C3D it truly is a great video descriptor, is a great feature generation for videos overall, and it generates and it outputs a very general features.
Okay, we've got 10 minutes until the bell. Shall we look at some code?
Yeah, I think so too, because Yeah, the paper, as I said, is very long, and it goes on and on because they describe different applications of their network for different tasks. They compare results with others, and so on and so on. It's all great. I really encourage you to read through it, as it is very, very interesting. But I think that the whole purpose of this is done. So you get the idea of what was the intention and how it looked like, how they came up with this idea, how they implemented it. And so I promise I have some code, and I do. So if you just briefly show you this thing. So the repo is out there on my GitHub account. The name is quite long, but yeah, you'll get it later from the recording. And so as part of this repo, I created some helper functions that would do the data preprocessing, that would create the model, for example. So I told you before that the model is implemented in basically 20 lines, and that is very much true. So this, in fact, is our whole model defined here. So total of five conv3D blocks here. Nothing fancy, but it works very well. What I can show you is this thing. So if I go to the notebook, this notebook basically takes you through the end-to-end pipeline of processing the videos, generating features, cropping, and all that stuff that you need to do for scoring purposes. I made it as convenient that you don't really need to do the whole pre-processing. I basically did it for you. It took hours to load all the videos and generate features and all that stuff. But it was so easy to do because I use a very clever library package called mpiple, which was invented by one of our colleagues in CSC. I can quickly show you one of the pipelines I use for generating features. So here, for example, I'm loading up all the frames for each video, and then I'm just running all those clips. First off, loosely evaluating them and processing for different steps, like extracting clips for each video using specific max frames or frames per clip parameters and frame step. Then doing center crop, pre-processing, so basically subtracting the mean or channel-wise mean for all the frames. Then running predictions in kind of a batch way here, running prediction on C3D pre-trained model, generating feature vectors, then averaging feature vectors for each long video, and caching them, so basically saving them back to a file. And these files, if you look into the folder here, each vector takes up only 17 kilobytes, and I actually saved them, and they can be reused. So in fact, if you go to the notebook and you have those feature vectors saved up in files, you can very quickly load them up just using this function, for example.
Can I just say just 30 seconds on mpiple? So it was written by Mitya Soshnikov in our group when we were working on some action detection projects. And the beauty of it is because for those of you that have done functional programming before or used F# or LINQ in C#, it allows you to write in this kind of functional programming way and building these kind of declarative pipelines. And it's so good for deep learning because it allows you to build this lazily evaluated stream of transformations. And it means means that you only ever have one thing running through the pipeline in memory at any one time. So you never run out of memory on the machine. You could be processing terabytes of data, and you're just doing one thing through the pipeline at once, and it's lazily evaluated. So it's absolutely beautiful. It's based on a library called Pipe by Julian Pallard, and then we built out this MPipe library. But I just posted a tutorial in the description. Definitely go and check it out. That this has revolutionized the way that we all write Python.
Oh yeah, absolutely, and I love it. It really helps a lot in all the pre-processing step and loading data and all. So yeah, as I said, we can, thanks to MPipe, we can really easily and very fast, in a very fast manner, we can load up all our feature vectors. Then we can split them using this test split parameter here. We can split them into train and test data sets, and run through PCA and SVM to perform classification. And like I said, the best performing model they did in this approach for outers, for example, for number of components of 500, achieved 82% of accuracy, whereas with this approach, I was able to get up to 78. With my implementation, I was able to get up to 78% accuracy, just using the pre-trained model that I found somewhere on GitHub, implemented by somebody else. So it wasn't really the same network or pre-trained network they used. So
just one quick comment as well. As you can see, we're using the SVM classifier, and the SVM, of course, is a binary classifier. It just kind of looks what side of the learned hyperplane are you on. So when you use SVM in scikit-learn for multi-class classification, it's doing a kind of one versus the rest. So what it's doing is it's building a model for every single class, and then it's learning a kind of confidence value, and that's probably the distance from the hyperplane. So it looks at all of your classes and it says, well, which one is most comfortably in the correct side of the hyperplane, and it will just take the maximum value, and that's the one that wins.
Yeah. So yep, and that's up there. As for network, one more thing worth mentioning here is, aside that we have this network definition here locked in a single function, I also created this small bit to help me get the video descriptor thing. So with this one, I just take the pre-trained model, I pop out 3 top layers to get to this FC6 layer, which generate the feature vectors. I load up pre-trained weights, and I just add a single L2 normalized layer on top of that, to match what they did in the paper. So you can find that on GitHub. Definitely, it's here.
So one of the really cool things about this is, because we're not even doing any fine tuning, this really is software 2.0.
Yeah, I'm just reusing a network that somebody else, trained, and I'm just taking it, loading it, running my data through it, getting the features, extracting the features, and running a classifier on top of that.
Okay, and so do we have any questions?
Oh, one other thing I forgot to mention, or I did mention that. We used a very, basically C3D was one of the approaches we played around with on a recent project with Delta Tray on shots detection in soccer matches. And it's interesting because I talked about, for example, UCF, which is kind of a short clips showing only a single action that we are supposed to recognize, right? Whereas here we were kind of detecting events, but we used the very same approach, or we played around with this approach. So we basically took this, like you can see here, on this timeline. It was almost 50 minutes of video, and we run inferencing on top of that video. And so we basically took some crops out of this video. We cropped out 16 frames, following some step guideline, and with that we basically run inferencing, then do some averaging, peak detection, and so on to basically detect the events rather than fitting in 16 seconds clip and just recognizing what's in there. So with that approach, you get a lot more false positives, right? Because you may have a lot of similar actions, or actions that look similar to shots but are not really shots. So it's in that kind of domain, it's always good to have this high level view on things like we see here on this timeline. Any comments, Tim?
Well, yeah, just exactly what you said, that, quite often we train these classifiers in quite a contrived, stratified setting. So we might be training it as a binary classifier, and we've we've selected positive examples from this huge space. And actually, these events might be rare. Shots on goal are very rare. So it's only when you run your model back in the real domain. So here on the football match, for example, you start to see that your model isn't actually 90% accurate like you thought. It's producing a whole bunch of false positives. And in this particular case, we had a very high recall. We had a recall of 100%, but the precision was a little bit lower. We were registering a lot of false positives, and we kind of addressed that by actually coming up with, by diversifying the model. We just found that by creating a simple ensemble, the precision got better. But it's quite interesting though, just to see a real world example of this being used.
Yeah.
So any folks on the call, any questions? Is anyone doing video action detection? I think it's super exciting because it's one of the prime examples of why deep learning is so amazing, because you can do all of these things in deep learning that you can't write code to do. And action detection just seems to be one of these things which is huge. It's so difficult to kind of annotate video. It's a kind of time consuming and error prone process. And this is an example of where we can use technology to help our customers kind of remove the drudgery out of a very kind of manual process. So I think there are so many use cases for action detection.
A quick question on frame rate. Is there any sort of benefit in choosing a different frame rate for different sports? So that, for instance, if you've got very fast action, you might want to be capturing every frame. But in other sports, you might want to take your frame rate down so that your 3D convolution is not every frame, but it's sort of every other frame or every third frame.
That's a really, really good question, and
very good point.
One of the biggest data augmentation techniques is to resample at different speeds, because if you think about it, all of these actions can happen at different speeds.
Mm-hmm. Yeah, and even for one of the experiments with this Delta Tray project on shots detection, I used an approach where we took these 5-second clips, and I only extracted 16 frames out of each of these 5-second clips. And these were not consecutive frames. These are basically frames that were selected with a step. So I took every nth or if frame out of these 5 seconds, which is total of 125 frames. So yeah, I was, and it still got very good results. In fact, for our case, for our task, it proved to be one of the best approaches for that. So yeah, there's definitely truth around that. Yeah.
And as we were saying earlier, all of the recent advances in action detection have been coming up with ways to improve the temporal domain. The spatial domain we seem to be well catered for already. So some of the approaches do skip connections between the frames in time, having a slow path and a fast path, or the architecture search one, or having a memory bank so you can have kind of long-term memories between events in over time. So almost all of the approaches seem to be really playing with time. That's where we're kind of making most of the ground at the moment.
Absolutely.
Any other questions, folks? Okay, well, in which case, Karol, it's been absolutely amazing. Thank you so much. This has been a fantastic paper call.
Thank you, Tim. Pleasure as always.
Yeah, and as I said, I'm super excited about action detection, because I think this is one of the areas where there are so many customer use cases, and also, you know, and I know the folks in the product team are building out loads of platform services for doing this kind of stuff. We already have things like the video indexer, but I know that there are some, you know, secret squirrels things in the production pipeline as well, coming soon. Anyway, have a fantastic rest of the week, folks, and we'll see you soon. Really appreciate you joining the call.
Thank you all.
Thank you.